Hello friends, Mrs. McBride coming to you live from my office here. What we're talking about today is the different types of energy. So we've already talked about these, but I just think it's nice to organize in this way. So the first type of energy that we have is kinetic. And you know that the kinetic energy is the energy of motion. Okay. And we know that kinetic energy is equal to 1/2 mv squared. But also, the other type of energy that we have that we haven't really talked about yet this year is potential energy. Okay, and we say that this right here is stored energy, or the energy of position. Okay, so there's really two different types of potential energy, if you remember from last year. The first one is called gravitational, and the second type is called elastic. So gravitational is, instead of the energy of motion, this is the energy of position. Meaning that if we change our position or get farther away from the surface of Earth, we're going to have more potential energy. And the gravitational potential energy is, remember, given by UG, and we know that UG is equal to MUG, or mgh. And the second type is the elastic potential energy, and this is the energy stored in a spring. Okay, and we called this, do you remember? US. This is U for potential energy, and then either G for gravitational or S for spring. Why would they call it elastic but then use an S? Good question. Let me know if you ever figure it out. Okay, and US is equal to 1/2 kx squared. Now, for those of you who have been paying attention, you might be saying to yourself, hey, isn't that the work done by a spring? It is. Remember, according to the work energy theorem, the work done is equal to the energy stored. Okay, so once we have these three different types of energy, we can now go ahead and well, actually, before we do that, let's just practice using some UG equals MUG. Okay, so quick example here. Let's calculate UG. We're going to do this a couple of different ways. So if this is my starting position, I am going to raise a ball to this position here. And I'm going to tell you that the height here is 2 meters. And let's say the mass is 20 kilograms of the ball. So my question to you is, what is the UG? Well, we know that UG is equal to mgh. So we could say that UG is really equal to 20. Our G is 10. And our height is 2. Or we could say that in this case, 20 times 10 times 2, let's go mental math wizards here. This is going to give us 400 joules. Okay, remember that in this case, or in all cases, energy is measured in joules. All right, same sort of thing, except now I'm going to take my ball and I'm going to roll it up a ramp. Okay, and I'm going to tell you that the ramp has a length of 50 meters and has a height of 2. Well, let's make this 5. It'll make more sense, right? That would be a really long ramp. And again, still same ball, 20 kilograms. So my question again is, what is the UG? Well, we know that UG is equal to mgh. So in this case, we know the mass is 20. And which one are we going to use here? Hopefully you're saying to yourself, hey, the height is 2. It's actually going to give us 20 times 10 times 2, or in this case, UG is also equal to 400 joules. All right, last one. Are you following the pattern here? We've got a ball and we brought it up to the top of the steps. The ball, 20 kilograms. The height is 2 meters. The total distance of all of these steps, let's say, is 7 meters. So what is the UGG? You guessed it, I hope, where you said that in this case, UGG is also equal to 400 joules. And the reason why we did this is twofold. Number one, I wanted some practice using UGG equals mgh. Number two, I wanted to be able to say that the gravitational potential energy is path independent, meaning that it doesn't matter which path you take, the energy is always the same. So again, it doesn't matter which path you take to get to a certain height. Okay. All right. And sort of last but not least here, we're going to take a look at the conservation of energy. And the conservation of energy just says that energy is neither created nor destroyed. It is only conserved. Okay, so we could write this out two different ways, where we could say the energy initial, or E naught, is equal to the energy final, or EF. Or what we could say, what I like to do, is say that the initial kinetic energy plus the initial potential energy has to equal the final kinetic energy plus the final potential energy plus Q. And again, remember this Q is just the energy lost. And I always recognize a conservation of energy problem by the fact that we have both a change in height and a change in speed. So if your problem has both a change in height and change in speed, then this might be your cue that we have a conservation of energy problem. Okay, so speaking of conservation of energy problems, here we go. Let's do one practice problem. I don't know about you, but I'm sort of feeling like it is a snowy day outside. So here is a hill, and here is a person on a sled. Apparently they have really long arms and their hair is blowing in the wind. Okay, so we might say to ourselves, well, what is the velocity of the person at the bottom? Okay, and what we really need to know is, well, what is the height that they start off at? Okay, what height do you want to pick? Let's say 20 meters. Everybody loves the number 20. And I'm not going to tell you what the mass of the person is. We don't need to know. Okay, so we'll start out with our K plus U, K naught plus U naught equals KF plus UF plus Q. And I will add that this is a frictionless snow hill. They must have put a lot of lubrication here on this sled. You know the scene from the Christmas Vacation? It must be something like that. I'll post the link for you. Okay. So first thing we're saying to ourselves is, say that this person starts from rest. So is there initial kinetic energy? Well, initially she's starting from rest, so is there initial potential energy? Yep, she's at a height. Okay, what type of potential energy does she have? Gravitational or elastic? She has gravitational potential energy because she's at a height. Okay, at the bottom, is there kinetic energy? Yes. Okay, because that's what we're looking for her velocity, so there must be kinetic energy. Is there potential energy here at the bottom? Nope, because she's not at a height. Is there energy loss due to Q? Energy loss due to friction, heat, air resistance, sound, etc. So now what I'm going to do is I'm going to say, well, UG is really mgh, and the kinetic energy is really 1/2 mv squared. I see a mass on both sides. So you must be saying to yourself, aha, this must be why Mrs. McBride did not give us that information. Okay, so if we plug in some numbers here, we know that little g is 10 and the h is 20 is going to equal 1/2 v squared. Okay, or this side gives us 200 equals 1/2 v. If we multiply both sides by 2, the 2's cancel out here, and this gives us 400 is equal to v squared. Let's do some mental math here. Or the square root of 400 gives us 20. All right, one more quick problem for you here. What happens if we have the same hill, but now at this point, I'm looking for something different, okay? So at this point, I don't want the speed at the bottom. I want the speed somewhere in the middle. So again, we'll say that this is frictionless. And here's my hill. Clearly it looks just like it. Here's my tobogganer. And I'm saying that this height is still 20. But in this case, now I want to know what is the velocity here. Okay, so what we have is we can say that K naught plus U naught equals KF plus UF plus Q. Now, how do I know this is a conservation of energy problem? Well, I see that there is a change in height and also a change in speed. So right now she's at rest, but at some point she's going to be going with some velocity. Okay, again, my first point that I'm going to look at is at the top here. The second point is somewhere in the middle. So at the top, does she have kinetic energy? Does she have potential energy? Yes, because she's at a height. Okay, at this point here where we're looking for the velocity, is there kinetic energy? Yes. Is there potential energy? Yes, but no Q because we're frictionless. So this is going to give us mgh equals 1/2 mv squared plus mgh. Okay, I like to cancel out the mass at this point. Okay, or we've got 10 times 20 is equal to 1/2 v squared plus 10 times 10. Or this is going to give me 200 is equal to 1/2 v squared plus, oh, this is 100. Subtract 100 to the other side, and we get that 100 is equal to 1/2 v squared. Okay, next thing we're going to do is multiply both sides by 2, where we get 200 is equal to v squared. And guess what? I have realized that I don't have a calculator. Uh-oh. So I'm going to just say, well, clearly the velocity at this point is the square root of 200 meters per second. Hopefully you guys are at home laughing at me and you are solving that for whatever the square root of 200 is. Okay? All right, good luck, friends.